Okay, in this video we're going to be talking about a new development connected with the Euclidean three-space, and we're going to spotlight in particular Descartes, something you can do with Descartes' default choice for the z-axis. Okay, what does that look like? What do I mean? Okay, Descartes says you have to have an x, a y, and a z component, x, y, and z, which in this case I'm going to relabel because I'm claiming I represent that this is only a default choice for the z direction. You'll see what I mean in just the next minute, I promise. I'm going to label this z sub y z, and I'm going to create a origin O and a destination point P, and I'm going to label it P sub y z as well. And I'm going to connect these two red reference points with a diagonal. Note, at this point we have a closed figure. I'm going to represent that this closed figure obeys Pythagoras. What do I mean by that? It just means the length of the red line segment obeys Pythagoras. In other words, the square root of the quantity x squared plus y squared plus z squared in quantity gives the length of the red line segment. Okay, so I've created something new here. Well, I don't know if it's new. I've created something, and it needs a name, and I'm going to call it a three-sided right triangle. Oops, no such thing exists. But this thing does exist that I've created here, and it does need a name. So if we can agree for now, I'm going to call it a three-sided right triangle. And now that I've done that and basically coined a new phrase, a new name for it, I've created something new and I've coined a new name for it, I'm not going to stop there. I'm going to transform this from its Euclidean three-space. I'm going to transform it into a closed figure in the xy plane. Okay, so how do I do that? Okay, moving on. Okay, I have taken the liberty of redrawing this, so I'm going to slip this whole thing to a new screen here. And I've done this because I don't want to clutter up the left-hand side figure. Okay, in this second frame here, I want to create a closed figure in the xy plane. And I represent that this is going to be a transformation of the thing that I'm now calling a three-sided right triangle in three-space. So, what does that look like? I'm going to transform this three-sided right triangle in three-space into a closed figure in the xy plane, or in two-space, xy two-space. So how do I do that? What does that look like? Okay, I'm going to very simply take and create what I'm going to call an axis of rotation with a red point center of a circle. Rotate the z-axis from its what I'm going to call its Descartes default direction. From point, I'm going to rotate point P around this red point with the red axis rotation. It'd look kind of like this. My circle's not so good, but anyway, the center of this circle is the red point. It's generated by rotating the default z direction around the red axis of rotation, which goes through the origin. And I'm going to represent that what I'm going to do is I'm going to rotate point P 90 degrees, and I'm going to represent that that's results in this point P here, a transform, I'm going to call a transformed P, transformed into the XY plane. So anyway, I guess I'll put this here representing 90 degrees. And I'm going to label this z-axis. This is the transformed z-axis. It's been transformed into the xy plane, so I'll label it z sub xy, which is just a more general direction, as opposed to the default special direction of Descartes in the three space. So this transformation of the z-axis is just a more general direction. And it happens to be, in this case, rotated 90 degrees from Descartes' default. And it preserves and allows me to have a closed figure when you consider me connecting the origin with this new transformed point P. Now I have a red closed figure here that is a transformation that obeys Pythagoras and is in every way, all of its constituent parts, exactly congruent with the original three-space system. So this is a two-space system that is exactly congruent with this three-space system, and I believe there's a term for that. I believe it's called covariant. I'm not sure, but I have to confirm this, but I believe that means that if you have a system and it's transformed, they both obey the same mathematical properties, and they're both in every way, all of their constituent forms congruent, that you have a state of where covariance is a property now of this system. So anyway, I'm going to bring both of these to where you can see them together. On the left, we have a three-space system. On the right, this red closed figure it's transformed in the xy plane, or two-space, and they're both, well, I'm going to say covariant. They're the property of covariance. Now, if I was to put some numbers to this, like, for example, 1/3 here, 2/3 there, and 2/3 here, then we could look at it this way. 1/3 squared plus 2/3 squared plus 2/3 squared, it does equal 1, because we have 1/9 plus 4/9 plus 4/9, that's 9/9, and that does equal 1. So now that I've gotten this far, I'm not going to stop. I'm going to continue on, and I'm going to add to this a third layer to this cake, so to speak. I'm going to move all of this over one more screen, and I'm going to redraw Descartes X, Y, and Z, and I'm going to draw in the blue diagonal from the origin O to the destination P sub Y, Z, because, again, this Descartes' default choice for the Y direction as we have seen, is just a specific direction for the z-axis. It can be generalized in any direction, as we've seen in the last slide. So I'm going to represent that. I'm going to change colors first. I'm going to represent that. I'm going to put in a black line here. And if you'll notice, if you can see it, there's a right triangle there. There's a 90-degree angle right here. And the blue line, as we have seen in the last frame, has a length of 1. The x component is 1/3. The y component is 2/3. And the default z direction component is also, z sub y, z, and that's also 2/3. So, in any right triangle, you can choose any side as the base. And if I choose the blue line or the hypotenuse to be the base, then I can draw an altitude to that base, which would be just a line segment from this XY vertex here, which I'm making a big black dot. So a line segment from that vertex over to, and I'm going to represent that is at a 90-degree angle right here, right there. I'm going to represent that that's an altitude to that hypotenuse. And using similar triangles, I'm going to let you pause this video and check and use similar triangles. It'll show you that the distance spanned across the origin and this reference point that I'm drawing in there, that this distance right here is x raised to the second power. And in this case, since this is 1/3, then this would be 1/9. Anyway, in order to keep this diagram from becoming too cluttered, this is an important juncture. Let's keep this in our mind and not forget. In order to continue and not clutter this diagram too much, though, I'm going to move to a new frame. So I'm going to slide this over and out of the way, and I'm going to redraw this thing again. X, Y, Z, and then a change of colors. And I'm going to put in my hypotenuse, my unit, in this case, a unit hypotenuse. And I'm going to represent that, well, let me see, I'm going to change colors again. Blue. I'm going to draw in a diagonal across the XY. Here's X component. Here's the Y component. And we have now a blue diagonal across the XY component, and it lies in the XY plane. And I'm going to represent that now we have a blue, a black, and a red triangle. It's a right triangle, actually, and there's a 90-degree angle right there. Now, this is what I call a unit triangle. just means it has a hypotenuse of length 1. And if I, again, choose the diagonal or the hypotenuse, the unit hypotenuse in this case, to have a unit length, I can choose it as the base of this new triangle. And as such, I can draw an altitude to that base from this YZ vertex, the vertex between the Y and Z, or at the juncture of the Y and Z components. So, as such, I can draw an altitude to the hypotenuse, treat the hypotenuse as a base again, and I can draw an altitude from this big red point. And I represent that it would look something like this. And I represent that it would create this large blue point. And I'm going to represent that, well, the distance between this large blue point and the destination P, in this case, P sub y, z, is z to the second power. Since z is equal to 2/3, then z to the second power would be 4/9. Okay, in order to keep this diagram from becoming too cluttered, I'm going to, now, at this juncture, okay, so you paused the video and you used similar triangles, and you're satisfied with the fact that this line segment, now symbolically labeled as z to the second power, has a value of 4/9. And you come back to the video, and now we're going to proceed in order to keep this diagram from becoming too cluttered. I'm going to redraw it and go from there. Okay, so here's Descartes X, Descartes Y, Descartes Default Z, and I'm going to change colors, and I'm going to draw in my unit hypotenuse. Here's the destination point P sub y, z, and here's the origin O. And so now I'm going to just put in the altitude from the YZ vertex, XY vertex. Here is the XY here's X, here's Y, and here's the vertex between them, and there was an altitude there in a previous frame, and there was an altitude. Okay, so now there's a second altitude here from the vertex between the Y and the Z. Here's Z sub YZ, the default Descartes direction for the Z axis in the YZ plane. And I have shown that there is an altitude here, and it creates two reference points, one blue reference point here and one blue reference point here. And as we have seen, and you have verified with similar triangles, the distance between the origin and the first blue reference point, the larger of the two, in this case now, was x to the second power. And as you have confirmed with similar triangles, the distance between the second smaller blue reference point and the destination point P sub YZ was Z to the second power. And you proved that, you confirmed that with similar triangles. Now, if we take we know that the length of the red line segment, the hypotenuse for this three-sided right triangle, as I'm calling it, and we've agreed that I can do that for now and for the purposes of this discussion. Excuse me. We see that there's a hole between the big blue point and the smaller blue point, and that's actually y to the second power. Now, that's a little bit more tricky to see because there's a triangle in there, but it's warped. But we do know that from mathematics that 1 minus 1/9 minus 4/9 is 4/9. So the distance in this gap here has to be 4/9. So I hadn't got this all completely worked out, but this should satisfy the fact that the length of this middle line segment is 4/9. And I'm going to call these three segments here components of unity. In other words, there are three numbers that add, three fractions that add to 1 or a unity. And that is the end of this discussion. It's a three-layer cake, basically. This is the third layer. And so what do I mean by that? It just means that there's altitudes that can be drawn that create reference points on the unit hypotenuse, and that these reference points, the large blue point and the smaller blue point, somehow have a magic property. Their property, which I'm identifying here, and I'm going to call this a lemma, that altitudes to a unit hypotenuse subdivide the unit hypotenuse into components of unity that have a mathematical relationship with their associated sides, where in the mathematical relationship of quantity and then like x, and then its associated component of unity, x to the second power. And for example, up here with z, with z up here, the component of unity that's associated with it is z to the second power. And here we have the component y and its associated component of unity, y to the second power. So anyway, in every right triangle, no matter how many dimensions it has, in a two-dimensional triangle, a three-dimensional triangle, the altitudes that can be drawn in from the intermediate vertices intermediate between the origin and the destination. Any vertices in between the origin and the destination point P are called, I will call them I'm calling them. They have to have a name, and if we can agree, I'm going to call them intermediate vertices. They all have associated with them altitudes to the unit hypotenuse. And it. Okay. So anyway, I've said all I'm going to say, except to say this in the next video. Well, in this video we did three space, three-dimensional right triangle, and we see that this three-dimensional right triangle can be transformed into a three-dimensional right into a two-dimensional right triangle that's exactly congruent in every way to what you're looking at here, and that it has all of its constituent components are exactly congruent to the components we see here, including the altitudes and the components of unity. So let's see what that would look like. I haven't shown that yet. Okay, so in order to keep this from becoming too cluttered, excuse me, I'm going to move all of this over and create a new screen. So I'm going to redraw this. Here's the X component. Here's the Y component. I'm going to draw a diagonal across X and Y. There's X and there's Y. I'm going to draw a diagonal across X and Y, and I'm going to put a large blue point there. And I'm going to create a right degree angle there. And I'm going to draw a line segment here out to the transformed P sub XY. In other words, what does that look like? The Z would have been, the default direction for Z would have been over here, out to destination P sub Y Z, and it had been rotated over 90 degrees to this transformed point P. Now what we have is and the emphasis in this diagram is the planar transform for the three-dimensional right triangle. This is a planar transform of that. Here we have a red line here that's a unit hypotenuse. It has a length of 1. In other words, you can use similar triangles in Pythagorean theorem and pause this video to confirm that for yourself. But if this is 1/3 and this is 2/3 and this is 2/3, over here would be 2/3 as well. You'll see that that this is mathematically true. So now what we're looking at is what we're putting the spotlight on in this frame is this two-dimensional transform of the three-dimensional right triangle that we've been talking about and laboring over. And you'll notice it has a beginning origin. Here's the origin O, and here's the destination P sub XY. And we have again we have what I'm calling what we've agreed to call two intermediate vertices. I guess I'll use black to use another color. Here is the intermediate vertex between the X and Y, and as such I can draw a altitude here 90 degrees, and I can transfer that over to the XY, to the unit hypotenuse. So so I've used this technique in order to run an altitude over to the unit hypotenuse, and it's this black line here and here, creating this reference point here. And the mathematics has it such that the distance between the origin and this first black reference point is exactly x to the second power, or 1/9. And I'm gonna let you pause the video, and you can or you can use a drafting program. I use AutoCAD Inventor suite. I drew this, and it does in fact equal 1/9, right down to, say, like in my case, 11 decimal places. Now, okay, continuing on. In black, we have I'm making a huge black point there at the YZ vertex. And I'm going to draw a altitude to the unit hypotenuse like this, with another black reference point. Now we've got a red unit length hypotenuse divided into 3 components. And I'm going to let you pause the video and confirm that this line segment here has a length of z to the second power, or in this case, 4/9. I'm really cluttering this up. Sorry. Actually, I guess what I could do, well, I could get rid of this. Oh. Okay, it's not allowing me to do that. Okay. I guess what I'll do is write it in red, so it'll contrast at least. 4/9. That's a little cluttered. But anyway, the line segment from P sub YZ, the transformed destination point, to downwards to the first black point below it, is 4/9. And again, with Inventor Suite accurate to 11 decimal places, we see that component, the top, what I'll call it, top of 3 components of unity there, is z squared, or 4/9. And the enemy, since we know that this is a unit hypotenuse of length 1, and we know that the bottom unit component of unity is 1/9. If we subtract 1/9 from unity, and then 4/9, the top component of unity, 4/9 from 1, we're left with, and I'll change colors here to, say, blue. Then by addition and subtraction, this would be 4/9 here, which is y squared, y to the second power. Okay, so anyway, now we've seen that kind of a thorough run-through with all this 3-layer cake. The first layer was simply to show to demonstrate a closed figure that obeyed Pythagoras, and we agreed that I could call it a three-dimensional right triangle. And then the second layer of the cake was to show that three-dimensional right triangle could be transformed into a two-dimensional transform that also obeyed Pythagoras, and also that every single constituent component of both the three-dimensional version and the two-dimensional transform were all exactly congruent pieces and angles as well, and that they both then had a property which we've identified as covariant. Just means, as a review for me, that we have a system, the three-dimensional system, closed figure, that obeys Pythagoras, and a two-dimensional closed system, or closed figure, that both obey Pythagoras and both have all of the constituent components being congruent. We have two systems, a three-dimensional system and a two-dimensional system, that have all of the same mathematical properties and geometric properties. So they're that's if you look it up, I believe that's a property, a mathematical property called covariance. It just means they exactly agree in a two-dimensional space, in a three-dimensional space, transform of it. So you can transform from the two-dimensional space around to the three-dimensional space simply by, and I'm going to change colors to red here, simply by rotating this z-axis, which is a more general direction for the z-axis. Rotate it 90 degrees, and now all of a sudden you are back to Descartes' default position for the direction for the z-axis. So, okay, I've said everything I'm going to say. Now the third layer of this three-layer cake is to add in all of the altitudes using this new lemma that I've created, where altitudes drawn from what we've agreed we can call intermediate vertices to the unit hypotenuse subdivide the hypotenuse, the unit hypotenuse, into components of unity that are fractions that add to 1. And anyway, that's the end of this video. Thank you very much. Oh, except to say this, the next video, well, in this video we did a three-dimensional right triangle and transformed it into a two-dimensional transform with the property of covariance between them. And in the previous video, we would have done a two-dimensional triangle, unit right triangle, and it has one altitude which subdivides the unit hypotenuse into two components of unity, x squared and y squared. So in the third video, which is to come yet, is going to be some very exciting stuff, because in that video we're going to have we're going to go into the next dimension. In this video it was 3 dimensions. In the next video it's going to be stepping off into the next higher dimension. And this really exciting stuff. Thank you. Okay, bye. Before we go to the next video, though, I will have to make this comment. I said we're going to go from the third dimension, which was the subject and spotlight of this video, and the next video is going to step off into the next higher dimension. Well, let me just say this. We cannot draw a four-dimensional object. But in this In this video, we've seen that we can draw a transform of a three-dimensional object. Okay, so what does that mean? What does that look like? In the next video, it simply means that while on the one hand, I cannot draw a four-dimensional right triangle because you just can't do it. But on the other hand, I've shown that you can draw the transform of a three-dimensional right triangle. So what we'll see in the next video is a transformed version of a four-dimensional right triangle. Okay, so what does that mean? It just simply means that in two-space, or the XY plane, I will show the transformed version of a four-dimensional right triangle transformed into the XY plane. Really exciting stuff. It obeys the Pythagorean theorem in every single way. And in its case, I'm going to have, well, in this case, in this video, I've shown that you have unit hypotenuse subdivided into three components of unity. And you can look at this frame here and see that. In the next video, the XY transform of a four-dimensional right triangle, which we cannot draw, has four components of unity with three intermediate vertices. Remember, looking at this diagram here, we have two intermediate vertices. So in the next video, we'll have three intermediate vertices and four components of unity. Really exciting stuff. Okay, thank you. Bye.